All right, so here is the solution to the last problem in the slides. So it says the circuit on the right, which I've got here, and I've got a bigger picture we're going to use in a moment, contains a low resistance mechanical battery that exerts a non-Coulomb force, FNC, to move electrons through the battery with negligible resistance. The end plates of the battery are very large compared to the distance of 0.1 L between the plates, allowing us to use that capacitor estimation. Two thin nichrome wires of length L, so here and here, and cross-sectional area A connect the battery to a thick nichrome wire of length 0.6 L right here, and a cross-sectional area 4A. The electron mobility of nichrome is U, and the N is the mobile electrons per cubic meter of nichrome. So we want to look at the electric field at 6 locations marked with X. We want to show the approximate distribution of charge on the surface of the nichrome wires, and then we're going to calculate the number of electrons that leave the battery every second in terms of L, A, N, U, and non-Coulomb force. All right, so to do the electric field, we need to just think of everything that we've learned. So the electric field here, it's going to be pointing away from the positive plate, and the electric field at this location is going to be pointing towards the negative plate, and this would continue around. Now, this is a thick wire, so it's going to have a much smaller electric field that would go this way. Again, following along and so forth. So the electric field is going to be bigger on these wires and smaller on this one. Okay, so in terms of the charge gradient distribution, so we're going to have a lot of positive charges around the positive plate and a lot of negative charges around the negative plate. And then these are going to become more and more dilute as we get to the middle and then build back up again. So basically the same picture that we've been seeing. All right, so those are the first two parts of that problem done. So big electric fields where the wires are, and then the thinner wires and a smaller electric field where we've got the cross-sectional area of 4A. If you do make a mistake like I did, then you can always write down what you mean by that arrow. Okay, now we want to calculate the number of electrons that leave the battery. Every second. So we want an electron rate, and we're going to use terms L, A, N, U, and force non-Coulomb. Okay. And I'll leave this picture up there so I can use it. So we're going to use current node rule. So NaUE1 is going to be equal to N 4 times the cross-sectional area UE2, because we know that that second electric field will scale accordingly. And delta V round trip is 0. So from here, we have force non-Coulomb over E times 0.1 L. So this is just the delta V we've talked about before, minus E1 L minus E2 0.6 L minus E1 L is equal to 0. So now we're just using the information that we've been given. So we're using our formulation for the battery, the two different lengths of wire that are the same, and the one that is thicker. Okay, so if we solve for E2 is equal to A over 4A times E1, which is equal to E1 over 4. So right now we have two equations and two unknowns. So one came from loop rule and one came from current node rule. So you should be seeing that when in doubt, start with these two things. So force non-Coulomb times 0.1 L E minus 2 E1 L minus E1 over 4, 0.6 L is equal to 0. E1 is equal to force non-Coulomb over E times 21.5. And we can then plug this in so that I, which is equal to NAU E1, is equal to NAU force non-Coulomb E over 21.5. Which is, now we have the number of electrons leaving the battery per second, because that is the definition of electron current. And if we wanted to, we could go ahead and solve for the electric field of the battery. So EB, so round trip potential must be 0. And so the electric field of the battery, 0.1 L minus 2 E1 L minus E1 over 4 times 0.6 L is equal to 0. The electric field of the battery is equal to 21.5 force non-Coulomb over E 21.5, which is equal to 21.5 of E1. So basically, all we're doing here is we're bringing together current node rule and loop rule and manipulating these equations to find what we're looking for.